Alright, so in this video, we're going to go over all the intermolecular forces that relate to what states of matter we generally find different substances in. So just go over molecular forces. This whole section, all it has to do with is the positive and negative forces being attracted to each other. So you really do have to know the difference between intramolecular and intermolecular forces. Intramolecular are our bonding forces. So our ionic bonds, our covalent bonds, our metallic bonds, those are all intramolecular. They're within the molecule. And we don't really use that with ionic just because they're not considered molecules, or with metals. We use it with covalent, but still it's the same concept. Any of our bondings are intramolecular. And so intramolecular forces are usually a lot stronger than intermolecular forces. Covalent bonds are always much stronger, and ionic bonds and metallic than your intermolecular forces. And that's because it's still all positive and negative, but that's because the positives and negatives are just so much closer to each other, and they're generally larger forces than our partial positives, partial negatives. So what you really have to know is that intra is within a molecule, has to do with the nuclei, the electrons, the different atoms in the molecule, how they relate to each other. And then intermolecular forces have to do with the forces between one molecule and another one of that same molecule, or another molecule that's different, but they have to be two different entities. So if you're looking at water, intramolecular forces would be the covalent bond between H and O. That's an intra. And then if you're still looking at water, an intermolecular force would be if you had another water molecule, and how do these two things relate to each other. So you have to know what they're talking about, because the intra is going to be responsible for its chemical properties. What does it behave like? Who does it react with? And then the inter is between two molecules, so it's in charge of the states of matter. Is it a solid, is it a liquid, or is it a gas? And all the states are how close the molecules are to each other, and that's what inter does, is how close are the molecules to each other. Do they want to stick together? Do they not want to stick together? So intermolecular forces are generally pretty weak because they are smaller charges, they're partial charges, and they're farther apart. They're between two different molecules instead of being within that same molecule. So you have to know the difference and what they're responsible for. Alright, so we've already looked at this, but we're going to look back again, and for 5th hour students, this is the one I promised I'd go back over again. Ionic compounds are held together by the Coulombic attraction. You have to know that phrase, but all it means is between the positive and negative attractions between ions that are sitting next to each other. So here's sodium chloride, and this ionic compound is held together by the fact that the sodium pluses, are attracted to the Cl negatives. And what you have to know about ionics is when you've got this one negative Cl, it's not just one Na plus that's attracted to it. All the Na pluses are attracted to it. And so that Na plus, that Na plus, that Na plus, on the other side you can't see it, but they build what's called a crystal lattice. And if you've ever seen a lattice structure in a garden, they're connected over and over and over, and they build up. This is a lattice structure because they build over and over and over, and you can kind of see it, that all the NAs are surrounding the Cl, and then from there the Cls are all, another Cl is surrounding that Na, and it builds over time. And so we don't usually use the term intramolecular for an ionic compound because it's not really a molecule. That's just a semantic. It's a formula unit. And so you may have seen that before. But these are really intramolecular forces. They're the bonding that's responsible for the chemical properties. So this one's the tricky one, but ionics are very, very strong bonds because they're layered over and over. That lattice structure is very difficult to break, and so the idea, I know that I gave 3rd hour, but I'd like to give 5th hour, is if you think about, if we've got one little water molecule here, this is the extent to which the H is attracted or connected to that O. And so if something were to come in here and try to break that apart, break that O off, it would be relatively easy. It's that single bond. And so if you think about this in people-wise, it's if, let's say we had two students, and they're just holding hands here. And so Red Rover, come on over, or whatever, and you send someone through that, how hard is it going to be to break that connection between those two people? And for some, depending on the people, that would obviously be a stronger connection than others, and that's where we get, like, our weak acids or strong acids. Sometimes that connection is stronger, but still, it's relatively weak, relatively easy to break. Even if those two people are very, very strong, it's not going to be that difficult to rip those two things apart. But then, what we get for ionic compounds is that this same bonding kind of structure happens over and over and over, and they're all webbed together. So if you take the same analogy with people hooking arms, think about it as, all right, you're hooking arms in a row across the entire classroom. Everybody's hooked arms, both arms, to somebody else. But think if you could also connect an arm backwards to the people behind you, to the row behind you, and then they connect behind them. People also connect up and down, and so we're all layered together in a giant human web. Now if you send something through there to try to break it, it's a lot harder to do because it's layered over and over and over. And that's what this lattice structure does, is it's very, very difficult to break. And so this lattice structure causes the ionic compounds to be very hard, rigid, they don't bend, and they're brittle. So you think about salt itself as a crystal, it breaks apart. And we grind our sea salt, it breaks apart, it doesn't bend. It's not malleable or ductile. So ionic compounds generally do not conduct electricity when they're solid. And you do have to understand this. Electricity is the ability for electrons to flow and move about. Well, if the charges are sitting here in this very rigid structure, the electrons are held very rigidly, and there's not any charges allowed to flow. But we can change this. We can change the conductivity of an ionic compound in two ways. We can either melt it, and what melting it does is it starts to break these bonds in between these a little bit, loosen those up, and lets those be a little bit apart from each other. Well, that'll let electrons flow when it's a molten liquid. And the other thing we can do is we can dissolve it in water, and if it's soluble, that means that water will break apart those bonds again and allow those Na pluses to be separate from the Cl negatives. So that's what we're doing when we dissolve this in water. The water gets in between these two, and it keeps them separate, which allows electricity to be conducted between the two different charges. And so you have to know that ionic compounds, electrons cannot flow very well when they're in solid form, rigid like this, but that they will start, if you melt it, you start breaking those by melting, putting heat in, or if you dissolve it in water and let the little H2O molecules come in between those two. And so what melting and boiling points are, which we're going to get into a whole lot, is how much energy does it take, melting is how much energy does it take to rip apart these bonds when they're in solid, to take them from being in an organized structure that's solid that we've seen the atoms very, very close to each other, and starting letting them be a little bit separate from each other. So there's our liquid. Well, to be able to rip these apart and make it a liquid, you're going to have to break the bonds in between these atoms. For an ionic compound, these bonds right here are pretty strong, and they're layered over and over and over, so it's very difficult for you to melt a solid. This is why we've talked about, have you ever seen molten salt? Well, probably not. It requires, I think, a melting point of like 801 degrees Celsius, something around that range. And then, again, if you would like to boil this salt, you've got to get those Na pluses and Cl negatives to be completely apart from each other, turn into the gaseous phase. Okay, and that's even harder to get these to completely separate from each other. The Na plus and the Cl negative really are very attracted to each other. And so ionic compounds, because they're pluses and negatives that are full-on pluses and negatives, not partials, they're very difficult to melt and very difficult to boil. So covalent compounds, on the other hand, kind of have a range, and it depends on what's going on in that compound. So again, when we talk about intra, those are the forces within a molecule, those have nothing to do with the states of matter. This has to do, intra has to do with what's it going to react with. Who's it going to break apart for completely. But intermolecular forces are the things that are responsible for states of matter. And that's what we're going to spend a whole lot of time talking about. So that's responsible for physical states, physical properties, which are solid, liquid, or gas. So covalent compounds are not lattice structured like ionic compounds. They don't connect over and over and over. So again, I'm going to draw water here. That's one water molecule, and it is independent of other water molecules as far as the bonding. They're not layered over and over and over. But what you're going to see is these different molecules are somewhat attracted to each other in different ways. And so one of the main ways that we're going to talk about is if the molecule is polar, that means it does have a kind of plus side and a kind of negative side, whereas ionic compounds have a full-on plus and a full-on negative. And so we know that in water, those are partially negative sides, and the hydrogens are partially positives. And so the intramolecular force are these bonds right here. Those are much, much stronger than the bonds I'm about to show, but the intermolecular forces are, okay, how does that molecule relate to that molecule? And so we know that for us, water is generally a liquid. Well, that means these two molecules have got to be relatively close to each other. There's our liquid water, as opposed to solid water, which we call ice. There's our solid, there's our liquid, and then to turn it into gaseous water, we have to boil it, get these different water molecules to be apart from each other. Well, since we know that water is a liquid, it means that these atoms or molecules are kind of attracted to each other. And that's what this intermolecular force is. And we're going to talk about how do you differentiate the intermolecular forces, what types there are, how strong are they. So that's what we're going to do with covalent compounds, is just determine how do those molecules relate to each other. Before we get into that, there is one group of covalent compounds that are really, really special. And they're called network covalent solids. And basically, it's a covalent compound kind of acting like an ionic compound in the fact that it creates a lattice structure. And so I do want to show you this. There's a couple versions that you're going to have to know, a couple compounds that do this. Probably the most familiar one to you is going to be diamond. So covalent compounds are supposed to be individual molecules, but a couple atoms will network covalently bond, and so it's kind of making a lattice out of a covalent compound. So if you take carbon likes to make 4 bonds, and so we put it with hydrogen, we put it with fluorine, whatever it is. But when we put it with another carbon, if we make these all carbons attached to it, well, these carbons on the end also want to make 4 bonds, and so they do so. Well, then what do they bond to? Well, if all we've got is carbon, then you can start to see that this starts building over and over and over, kind of like our lattice structure with ionic compounds. And so this should start looking like an ionic compound. Well, what do we know about ionic compounds is that that structure is very strong. And so these covalent substances, we call them network covalent solids because they create this network, but they act kind of like ionics in the fact that they're very, very difficult to melt or boil. It's very difficult to rip this all apart. It's a 3-dimensional structure all the way through, just like that salt was. And so that's what diamond is, and you should know that diamond is very, very hard. It's the hardest substance that we have on Earth, I believe. And so why it is so hard is that these carbons are covalently bonded to each other 3-dimensionally through space, and so we call that a network covalent solid. So carbon does this, and the other element that you're going to need to know that does this is silicon, which is sitting right underneath carbon on the periodic table. It also wants to make 4 bonds. So we see things like just plain silicone, and then we also see silicon dioxide, which for us is glass or sand in different forms. But silicon dioxide does it as well. And so there's not many that you have to memorize exactly what they are, but you should know that carbon and silicone do this primarily. And why they do it is they can bond 4 times and build this lattice that goes over and over and over. And then that's very, very hard and very difficult to break. So this is, chemists would get mad at me for saying this, but this is kind of like a covalent ionic compound. It behaves like that. in its strength and difficulty to boil. So those are a few that behave like ionic, but the rest of the covalents we got to talk about. Well, what do they behave like? Do they stick together like water and are liquid? Are they way apart like gases, like carbon dioxide? Do they actually become a solid that they're so attracted to each other? So I just want to show you the bonding comparisons, just to give you an idea before we get to intermolecular. These are our intramolecular forces. So these are our bonds and the relative strength. So ionics, we get between 400 to 4,000 kilojoules per mole. That's a straight-on positive with a negative. Covalent compounds depends on the size of the atom and the electronegativity of each atom, but they're sharing electrons, and their range is from 150 to 1100. So we do get some covalent compounds that are actually harder to break or rip apart than ionic compounds. It just depends what the atoms involved are. And then we have metallic bonds, which are cations or pluses with that delocalized electron C that we talked about. And so some of these are very easy to break apart, and these kind of range almost along with covalent. So those are all intramolecular forces. Those do not get broken with changes of states of matter. Okay, with the exception of this guy, because that's the only bond it's got. It's both intra and inter, and we'll kind of look at that when we start comparing the different things. Alright, so now we're going to get into intermolecular forces. So there are several types, and they're of varying strength, what we're dealing with here. So we're going to kind of go through them one at a time and talk about what they are. And the names actually do a pretty good job, at least 3 of them, do a pretty good job of explaining what's going on. I think the hydrogen bonding is kind of a terrible name. It gets people very confusing. And then London dispersion doesn't help you know what that is until you kind of see a picture of it. Okay, so the first one is ion dipole. Okay, and so you got to know what each one of these things is, an ion and a dipole. An ion is the plus or negative, the fully plus or negative, and this is a polar compound that has a partial plus and partial negative to it. And so it says, all right, how does a full-on plus negative relate to a partial plus negative? Okay, and well, there is an attraction, so the negative part, the full-on negative anion, will be attracted to the partially positive side of a polar molecule. And then the cation, the fully positive part, will be attracted to the partially negative end. And so you were actually asked to draw this on the free response that we took last week with lithium chloride and how it breaks up. And so you were asked to put water in between. Well, water we know is polar, and oxygen is our partially negative side. Hydrogens are partially positive. So the water molecules are going to orient themselves like this around the lithium, just because pluses attract negatives. Sorry, that's not written very well. Okay, and so the same thing happens on our chloride ion. If we take a water molecule, the partially positive hydrogens are going to be attracted to the full-on negative chlorine, and they'll surround that as well. So hydrogen, draw a couple more. And so something they really want you to know is, what makes this thing soluble? Why does lithium chloride split up in water? And it's the fact that water can actually get in between these two and separate them. The Li and the Cl, this positive and this negative, are still attracted to each other. It's just the fact that there's enough water that's in the way to keep them apart. If you let the solution of lithium chloride or salt water, if you let that water evaporate and those things go away, the Li and Cl are going to come right back together. It's all a battle between positives and negatives, that attraction, and what's in between those. Okay, so you do have to know this is an ion dipole. That is an ion, that's a plus ion, and that's a polar molecule, and they're attracted to each other. Okay? And so the dissolving in water is a big part of this part. Okay, so what it means for something that's insoluble, if we think about AgCl, that is generally called an insoluble compound. Now, we did some KSP stuff where that does split up a little tiny bit. But generally that sticks together, and all that means is that Ag plus and that Cl negative, well, they're too attracted to each other to be able to split up by water. Water's not able to come in here and split that attraction apart. But for some of them, that attraction can be broken by enough water. Alright, so the next one is dipole-dipole forces. And all you need to think about this is convert that dipole in your head to polar with a polar. So that's two polar molecules. How do they attract? So polar has partially positive and partially negative. And so it would make sense that the partially positive part would attract the partially negative part on another molecule. And then this partially positive would attract that partially negative on another molecule. But you got to have two different molecules for this to happen. And so I believe that this could be HF. It may be HCl here with the sizes. Not that we care all that much. But this is definitely a polar molecule where the F is the negative part. Okay, and hydrogen is the positive part. Okay. Sorry, I'm drawing these all the way around. And so let's look at all the forces involved here. So anytime you get a positive next to a negative, that force right there is going to be attractive. So if you look around, anytime the positive and the negative are sitting next to each other, that's an attractive force. That's going to keep them together. So here we see again. But then what happens if you get the negative sitting next to the negative? Well, those are going to repel. So that's not going to stick those molecules together. Those are going to try to push apart. Those ends are always going to try to push apart right there. That's the repulsive force. And so there are repulsive forces in these dipole-dipoles, but we're trying to talk about whether they stick together, these molecules, or do they separate? What kind of phases are they going to be? So HF here would be able to stick together if the molecules orient themselves in an attractive manner. And just like magnets, if you try to shove these two that have the same pole together, they're going to push apart. But if you get magnets where the opposite poles are, two polar things, then they're going to be able to stick together. Okay? And so, just like magnets, if you were played with stronger magnets versus weaker magnets, the greater that dipole moment, the greater the force between the molecules. Right? So they'd be able to either repel each other stronger or stick together stronger. So if you've had really strong magnets, when you get them really close, they either stick together really well or they push apart really hard. Versus if you've gotten some weaker magnets, you can feel a little bit of repulsion, a little bit of attraction, but it's not as strong. So we got to talk about what does this do to our boiling and our melting point. So when this force happens, this attractive force happens, it keeps these two molecules stuck together. It makes it that much harder to boil it, which just means, or melt it, which just means separate those two. And so the stronger that force is between, the harder it's going to be to boil. And so what we read with that, or what we understand with that, is it will have a higher boiling point. Okay. So the next one is hydrogen bonding, which is kind of a misnomer. It makes sense once you understand what it is, but it's kind of unfortunate when we're first learning it. But all hydrogen bonding is a very special type of dipole-dipole force. So it's got to be polar with polar. Okay? But what has to happen is you must have a hydrogen atom bonded to a small, highly electronegative atom. So what we're going to decode that as is either N, O, or F. And so in the past, my students have generally remembered this as F-No. You have an H atom directly attached to one of those. Then hydrogen bonding will be able to occur. And so why that happens is if you have, let's say, H attached to an F here. Okay, we've gone over that this is polar, that the negative goes toward the F, because F is very electronegative. Okay, then again, if you have H with, let's say, Br here, this right here, we actually probably have to look it up because I'm not quite sure how they rank, but I think that might end up being a little negative and not a little bit positive. So again, it will go toward the bromine and away from the hydrogen. But because fluorine is so electronegative, this is actually a much bigger polarity swing, because that's much, much more attractive than the H versus the Br, they're a little bit closer. And so what this ends up being, and this is a simplified way of looking at this, but kind of a big partial negative, almost all the way negative. It's almost ionic, and this would be a big partial positive. And so what this leads to is if you have another one of these guys with a big partial negative and a big partial positive, you're still going to have that same attraction between the H and the F that we had before, okay, between any two polar. But because those are big forces, almost fully positive, almost fully negative, that is particularly strong. Where if it was something where they were not, just a little bit negative and just a little bit positive, if you got another one, yeah, they would be attracted to each other, okay, in between here, but it's not as strong. This is weaker. And so hydrogen bonding is just a special type that comes when hydrogen is directly bound, it's got to be connected, to an N, O, or F. And we use these three elements because they are very small, which means their nuclei is pretty close to the electrons, and they're very electronegative, which means they're going to pull those electrons very strongly, and so that's going to lead to a bigger partial negative. And so that leads to hydrogen being a bigger partial positive, which makes this very polar. And that's all we're doing with this, is it's a special kind of dipole-dipole, polar-polar, where the things involved are very polar. And so it makes these things pretty strong, the hydrogen bond, pretty strong. And so this is, if you took AP Bio, this is really important in water, and it's also really important in our DNA. So why this misnomer happens is people want to call the bond between the H and the F right here, that is not the hydrogen bond. The hydrogen bond is the bond or not the bond, but the intermolecular force in between the two molecules. So it is actually the intermolecular force. That right there between the H and the F up here is an intramolecular force. That is just a covalent bond. Versus the hydrogen bond is not a real bond, it's an intermolecular force. And so when we look at two water molecules, we know that oxygen is negative and hydrogens are positive. And so the hydrogen bond actually occurs in between the oxygen and the hydrogen on different molecules. So you have to get an intermolecular forces on different molecules. Right? So we're going to practice some to see if hydrogen bonding is actually present in this molecule. So hydrogen bonding is just a special, very strong type of dipole-dipole. And so what that's going to do is lead to higher boiling points, higher melting points. It's harder to make it a gas or a liquid as opposed to some other things. And so the key is H has got to be bonded to F, N, or O, but that right there, that H bonded, is not the hydrogen bond. The hydrogen bond is what occurs between two different molecules. So I'm going to go ahead and draw two molecules of each of these and talk about whether they can hydrogen bond. So if we take ethane, the carbons bond to each other in a chain. There's ethane. And so from here on out, I'm just going to draw lines coming out from the carbons like this to indicate the H's, just because it's going to end up taking me a while to draw all the H's. So that's one molecule of ethane. So if I took another molecule of ethane, we have to decide, okay, first of all, is this molecule capable of hydrogen bonding? So to be capable of hydrogen bonding, you have to have a hydrogen bonded to an FN or O. Well, there is no FN or O in either of these molecules, so this cannot hydrogen bond. But I also want to talk about whether these things were polar to begin with. Both of these are non-polar molecules. They are symmetrical all the way around. There's no side that looks particularly different than any other side. And so we can't draw a partially positive and a partially negative on this. So these two molecules are going to be very difficult to get to stick together. And so if you had to guess on a state of matter for ethane, if they're not going to stick together, they're going to be a gas. That's our state that doesn't stick together. Okay, but these cannot hydrogen bond. Alright, Alright, so then we're going to go to methanol. Right here we have C with 3 H's on it, and then an O and an H. And again, these little lines sticking up are just representing hydrogens. Okay, so I'm going to draw 2 of these. And so we have to determine, is this molecule capable of hydrogen bonding? Well, we have a hydrogen bonded to an F, N, or O. That right there is our hydrogen that is going to make this capable of hydrogen bonding. Now remember, there really are hydrogens sitting right here that I just didn't draw in, but these are not capable of hydrogen bonding because they are not attached to an F, N, or O. So this is our hydrogen bonding hydrogen, but what you have to make sure you don't say is that is not the hydrogen bond. The hydrogen bond must be an intermolecular force. So we've got to determine, okay, how would 2 of these molecules actually interact with each other? Well, if we looked at this, this is going to be a polar molecule. There is something that's different. It's not symmetrical. And so what we have to look at is O is actually our most electronegative element. And it's going to drag negatives in from this side, and it's going to drag negatives in from that side. And then we have our lone pairs, so this guy's going to be negative. And both of these are going to be positive. But the H in particular, it didn't have any other H's or any electrons. It only had 1 electron, and it was pulled in by the oxygen there. Okay, so if our oxygen's very negative, and we drew the same thing over here, very positive, okay, and then these guys, this whole blob would be somewhat positive. But figure out how these would interact. Well, right now, the way I've got them lined up, they wouldn't really interact that way. And so I'm going to try. I don't know how well I'll do. Okay, I flipped it around. Alright, and so let me delete that out of there. And then let's move this guy up. So I just reversed it around. And now if you look at what I've got that negative that was on my oxygen down here. This negative is now attracted to this positive, right? And this negative is attracted to this positive. So that right there is the hydrogen bond. And that right there is a hydrogen bond. It is the attraction between 2 molecules. That hydrogen is capable of hydrogen bonding. It's attached to the O. And that hydrogen is also capable of hydrogen bonding. So the hydrogen bond is actually between these 2 molecules. So if you had to guess on a state of matter of methanol, you might guess, they're going to stick together a little bit. So that might be a liquid. Okay. Alright, and if we actually do look at the boiling point, I went and looked them up, the boiling point of methanol is 65 degrees Celsius, which would make it a liquid because room temperature is around 20 degrees Celsius. So it does make a liquid because these are held together. I also went and looked up the boiling point of ethane, which is negative 89 degrees Celsius, which makes it a gas at room temperature. Remember, those molecules were nonpolar. They didn't stick together very well. Alright, so we're going to move on to acetamide. So I'm going to draw the molecule here on 3 and get this thing to work. We have C, 3 H's, C, double bond. And don't worry about necessarily drawing these, though if you are watching this, you look at the order, because these were a problem for us on our mock exam, our free response that we just did. The compound usually gives the order in which they go, and so I know that carbon has to be bonded 4 times. Usually if it's sitting next to an O and then something else, that O is going to come off one direction of it, like I showed the double bond. So here we go. We're looking at this molecule that I drew twice, and so we ask, is it capable of hydrogen bonding? So does it have a hydrogen bonded to an F, N, or O? Yes, it does. And the hydrogens that are hydrogen bonding capable, that one and that one, they're the ones attached directly to an N. The hydrogens over here attached to the carbon are hydrogens, but they're not capable of hydrogen bonding because they're attached to that carbon which doesn't pull their electrons very much. It doesn't make them very positive. Whereas the nitrogen pulls a whole lot and makes these very positive. And so we are capable of hydrogen bonding. And so we've got to imagine where the hydrogen bond would happen. So if you have these two molecules, that nitrogen is going to be very negative. And so the other thing, that bond that could happen is between that positive, I'm not going to take the time to rotate these anymore, but between that positive or that negative and that positive. The other thing that can happen is, something I didn't draw was the lone pair sitting on oxygen. These hydrogens, since they're very positive, can also attach to that negative. So what the hydrogen is attached to is not necessarily as important as what they are attached to for the hydrogen bonding. They have to become very positive because they're attached to something very, very electronegative. But then once they're partially positive, they're attracted to anything that's negative. And so that oxygen will be negative, the nitrogen will be negative, so they're going to hook together, and they're going to, these two molecules are going to stick together pretty well because they're going to be attracted. They have all kinds of positives and negatives. And so they have hydrogen bonding, so these are the hydrogen bonds in between the two molecules. So I looked at the boiling point for acetamide, and the boiling point is 221 degrees Celsius. Much larger than methanol's was. This has lots of options for polarity to hook together. Alright, so we're going to go on to the next one, which I believe is acetic acid. If you rewrote that, HC2H3O2. So if we go ahead and draw this molecule in the order it says, CH3, C, double bond to O, then coming off an O and an H. And I'm going to go ahead and draw the lone pairs on there. So we have another one of these, and I'm going to go ahead and draw it backwards, just so we can connect them a little better. Alright, we have our lone pairs. And then we ask ourselves, is this molecule, it's each one of these, are they capable of hydrogen bonding? Do they have a hydrogen bonded to an F, N, or O? Yep, that's a capable of hydrogen bonding, that's capable of hydrogen bonding. None of the other hydrogens, which are not shown here, these are not capable. Okay, but that's our hydrogen bonding one, so that's going to make that very positive, make that very negative. So very positive and very negative. That oxygen sitting up here is still negative. It's one of our three most electronegative elements. Okay, and so if you ask yourself, can these attach to each other? Are those attracted to each other? Are they going to stick together? Well, that can stick together there, or it can stick together there, and this can stick together here, or if it was up top, it would stick together to the oxygen. So if you ask yourself, okay, well, what state of matter are these going to be? Are they going to stick together, or are they going to be far apart? Well, these are going to stick together, and here's the boiling point, 118 degrees Celsius, higher than water to boil this thing. So it's all because of these hydrogen bonds in between. They're just very special intermolecular forces that are particularly strong. Alright, so next one. I'm going to go ahead and put check marks to the ones we said, that one can hydrogen bond, that one can hydrogen bond, that one can hydrogen bond. And that was a no. So then we come up with methanol, or ethanol, sorry. That is our drinking alcohol, or the alcohol that's in our cars for some reason. Alright, so we've got one of those. And another one of them. And so, is this ethanol capable of hydrogen bonding? And yes, it is. It can hydrogen bond. This guy is capable right here, which makes it very positive. It's very negative. And so the attraction that can happen, the actual hydrogen bond, would be in between those, or between those. And the molecules would orient themselves. They would move about where I started off with rotating so that they would be in the right position to be attracted. Okay, so those would attract each other right there. And so if you look, and this is not quite dead on, we're going to get some different things with this, but the boiling point is 78 degrees Celsius at room temperature. It's a liquid. But if you compare that to the one right above the boiling point, this one has a lower boiling point, which means it's easier to separate these two than the other ones. And if you think about when we drew acetic acid, we had this extra O that was also negative that we could attach to. So there were lots of places that we could attach to and make these intermolecular force connections. And so the more of those that there are, and the stronger they are, the the more likely it is going to be a liquid. The atoms are going to stick together. Alright, so that one was capable of hydrogen bonding. Put a check mark there. And then last one, I believe this is acetone. So we have C, H3, C, double bond O, another C, H3, C, H3, C, double bond O, C, 3 H's. Alright, so we'll put the lone pairs on there. So there are hydrogens all over this atom or molecule. Is this molecule capable of hydrogen bonding? And the answer is no. Okay, because there is no hydrogen attached to an F, N, or O directly. That doesn't mean it's not polar, it just means it's not this special case. So it cannot hydrogen bond, but this molecule is still polar. We've got two sides that look identical, but then we've got this O that throws off the symmetry, and so this side is partially negative. We've got these lone pairs, plus O draws up the electrons to it anyway. So we've got a partially negative thing here, which means the rest of this blob somehow have a partially positive. So down here in this other molecule, we'd have a partially negative there and a partially positive here. So would these two molecules be attracted to each other? Yes, we'd have that negative to that positive, but that's not a hydrogen bond. That's just a dipole, the generic polar to polar. And they are attracted to each other, they're going to be able to stick together. But if you look at their boiling point, it's 56 degrees Celsius. That's lower than anything other than the ethane that we've seen. And all this was to go through. There are a few other factors that go into this, but hydrogen bonding is a very special, very strong intermolecular force that leads to higher boiling points. It makes it harder for them to be separated. Alright, so if we actually look at some graphs of some common compounds, we'll look at this first one about hydrogen with the group 6A. So group 6A starts with oxygen, sulfur, then we got selenium, then we got tellurium. And so those are all our two negatives. But if we put hydrogen with them, if you notice there's two hydrogens for each one, they're going to need two bonds for each one. And if you look at their boiling points, these are how hard is it to separate one molecule of water from another water molecule. Okay, so we said it takes 100 degrees Celsius. That's the amount of energy we've got to put in temperature. Okay, and so that's to separate one water molecule from another water molecule. So this boiling point is to tell you how hard it is to break that right there. It does not make it not water anymore. It does not touch either of these. That is not what boiling is. And so H2S would be, okay, we've got H with the S's. And the question for it to boil is, alright, how hard is it to break that right there, that intermolecular force? And so if you look, keep going, we've got H with Se and H with Se. And so the next thing on this graph would be, alright, how hard is it to break that connection right there? That's what the boiling is it's breaking intermolecular forces. So if you look at this graph, for some reason, it's a whole lot harder to break this one right here than it is that one or that one. Well, in all of these, they have the same kind of structure. We're going to have two lone pairs sitting on that central atom because that whole column has 6 electrons. Okay, so the question is, why is it so much harder to break that intermolecular force with water than it is with H2S or H2SE? And the answer is, that is particularly strong. That's hydrogen bonding, which is just a very strong version of dipole-dipole, very polar. And so if you look going down on this graph, these top 3, okay, again, they're just in a row, HF with HCl, HBr, HI, those are a lot higher than they should be compared to the rest of the graph. Everybody else is kind of going up as you go down the periodic table, and we're going to talk about why that is, except for these 3. And if you look what they have H with an O, H with an F, H with an N. And that's our hydrogen bonding, F-No. So hydrogen bonding leads to oddly large boiling points versus where they're supposed to be otherwise. and that keeps them liquid longer. And so this is why it's very important. Hydrogen bonding is why water exists as a liquid, and why kind of we exist, because we need water to be a liquid. Alright, so this next one